Hello and welcome to our webinar Beyond Unit Tests. I'm Thomas Schütz. So why do we want to do something more than unit tests? Let's have a look at the costs of testing. If we test too late in the process or late in the process, the tests get more and more expensive. So unit tests is relatively inexpensive, so that's good, of course. It's fast, it's early in the process. The later you get in the process, the more expensive and the longer the tests run take. So what we want is we need to learn and test earlier. So we want to bring all the tests as near as to the implementation as possible to get a fast response to save costs. Let's have a look at the development process for a typical embedded systems. We usually start with an evaluation board. We configure the drivers, we test the drivers, then we create hardware-related software components, for example, motor control or bus-related protocols, low-level bus protocols like CAN, LIN, and so on. On top of that, we have usually software components that define the application logic. We integrate everything to an application, and eventually we move to the real hardware, to the real electronic control unit. So, and the question is, where do we test, or where can we test? The usual points where tests are done are in the early process, the unit tests. Unit tests have the disadvantage you can mainly test software components. It's really hard to test something else than pure software components. The advantage is it's early, it's cheap, so please do that. Later in the process, you need a system test and maybe also a hardware-in-the-loop system test, or a simulated system test. That's a very good thing, but it's usually very late in the process and it's very expensive. So what do we do? With our mini-hill, we can get part of the system test and the complete hardware-software integration test to the early phases of the development. So, for example, you can test the complete software stack, including the drivers, the motor control, the battery control, and all the application logic on top of your real processor in one go. So as a black box test, that's the idea. By that, bringing a lot of the late tests to the desktop of the developer. So most embedded projects are not tested or not tested very deep in the early phases. So what do I really want and need? You want to test what is changed most frequently, and that's your software. You change your hardware. For example, if you have a big hardware in the loop or system test, you change your hardware every couple of weeks or months even. So why do you need to test a complete system? So why do you need to test all your motors and so on in the loop? You need to test your software because that's what is changed most frequently. We want to test every code change for every developer within minutes instead of weeks. Because why every code change? Because if you change something, you need a regression test, a full regression test, because you change something over here and something happens over there. You didn't even change something there, but you have side effects. You have limited resources and so on and so on. So that's why you need a full regression test for every code change. Then it's very good to have full test automation to enforce tests and to save time and money. So for example, by using continuous integration. So every test should be able to run on continuous integration. And you need an automated hardware-in-the-loop test to test more than pure software units. With a unit test, pure software units, but that's just not enough. So let's have a look at the focus of the test levels and methods. If you have a look at the ECU, so electronic control unit, Usually you have a microcontroller on the electronic control unit that runs your application software with the drivers. Then you have power electronics, sensors, actuators, and so on. And they all control the motor, the pump, the hydraulic system, whatever your system is. And usually it's really cheap to write unit tests, software integration tests. You can use the unit test tool to do that. They're easy to automate and so on. But if you want to test everything, it's a lot of work, still a lot of work. And you cannot test every unit. So for example, a motor controller for a loopback control, that's really hard to test with a unit test tool. So you need something more. Let's have a look at the next step. The next step would be the smallest possible hardware in the loop test. So we call this a hardware software integration test. We look at the microcontroller as a black box, including the whole software stack, all the drivers and so on the real microcontroller. So that's your black box. And we test with the mini-hill exactly this black box. So the next step would be a big hardware in the loop test, including power electronics, sensors, actuators, so even part of the system. That's already a lot of effort and usually very late in the process. And it's not run very often because it's so much effort. The biggest effort usually is a real system test. So you include the real system elements like a motor, pump, hydraulic system, or you get into the car and drive around the block, whatever is your system. And that's a lot of work and is therefore not done very often. A couple of times maybe in your project. So let's have a look at a different kind of tests, static code analysis. For example, usually you can apply this for software, for pure software units. You can do also reviews. That's also a test method. So basically having a look at the code. Somebody else has a look at the code. Then you can do manual tests. That's done very often in embedded systems because it's so hard to automate the tests for embedded systems. And they take a very, very long time usually. And they're really hard to repeat. So the effort increases exponentially from unit tests to system test. And unit tests, software integration tests, and also the hardware software integration tests, they are really easy to automate with continuous integration. A big hardware in the loop test or a system test, they are really hard to automate with continuous integration. Okay. Hardware in the loop test you can automate. The problem is it's so expensive that it's never free for automation. So the continuous integration needs the hardware in the loop test stand attached to it. So it cannot be used for anything else. So that's often a problem with hardware in the loop test stands. So what are the typical response time for the test levels? The unit tests are typically in the range of minutes, 5 minutes, 10 minutes, up to an hour. Then the hardware software integration tests are usually not done. That's the big gap here. System tests usually is done every couple of weeks, even every couple of months, depending on the system. And the acceptance test is on system level, so it's usually also not done more often than a system test. So speed is the message. We need fast response time to really react fast, to develop fast, to find the bugs fast. So we need the unit tests for fast response and on software level. And then we need hardware software integration tests. With the mini-hill, you can run them also in a couple of minutes. After every commit, for example, you can run the test. If you have longer running tests, you split it up in short running tests and long running tests and let the longer running tests run overnight. That's easy to do manually or with continuous integration, doesn't really matter. So what do you need to test an embedded system? You need, or any component in an embedded system, you need a test harness for your embedded system. Your system under test can be a system, a component under test, so a single unit. In this case, it's a unit test you need. A system, you need a system test or an integration of components, then you have an integration test. And for a unit test usually is a synchronous test. So you step by step execute functions and evaluate the return values. But on one end you need the test case, on the other end you need stubs and mocks. That's very important because your component doesn't even compile without satisfying the interfaces at the other end. So all those includes and so on. So you need stubs and mocks, and you need synchronous test cases. That's relatively simple to do. The problem is if you want to go into integrations and system tests, you need asynchronous tests because a lot of things are happening in parallel. While your motor is running, the CAN bus does something, or while the motor is running, the battery is charged, or whatever it is. So you need asynchronous tests, and you also usually do not get away with stubs and mocks. You need closed and open loop simulations. For example, if the system expects a motor, because it's a motor control system, you need to simulate the motor, because if it's not attached to the system, your system fails immediately and you do not even get to the point where you actually can test something. So you need asynchronous test cases because a lot of things are happening in parallel, and you need closed or even or open loop simulations. So closed loop simulation, for example, for a motor control, you need a real simulated motor. And an open loop simulation is, for example, if you play back signals and things like that. So without reaction, without the interaction directly between the system under test and the test system. So you need more than test cases. What can you do now with the hardware-software integration test? The main goal is not to test a single component, for example, the motor control, but the integration of the components with the software system, including the drivers and electric signals. So you want to know how they interact. You can put your system in almost any state to test it by changing the simulation for failure injection. So for example, if you want to test for a certain temperature, just change the signal of the temperature. You have the interface, so to change it, so you have a simulation. Or if you want to check whether a motor reacts correct on a certain failure of signals, change the motor simulation to fail. And this enables automation, speed and depth in your test process. So a concrete example, again, we have the black box, the microcontroller, with your complete application software, with all the drivers on the real microcontroller. That's really in your application. In this case, I want to show you how a shutdown path for temperature can be tested. So the temperature monitoring is attached to the ADC. So we inject a wrong temperature by providing an analog value, a wrong analog value. Then the signals or the events cascade through your system. Because it's a black box test, I'm not interested in that. But what I'm interested in is I want to know whether after 100 microseconds, for example, the PWM is off, because it's a safety critical function. That's what I want to, that's something I expect. And the other thing I expect in this case is a correct CAN error message. So I want the system to know that it actually failed, and to propagate this to other systems. How do we do that? Let's start with a hardware setup with our mini-hill board. That's about a one sheet of paper size-wise. On the right side, you have the system under test. That's in this case a STM32 microcontroller. Can be any microcontroller, 3.3, 5 volt, doesn't matter, 16, 8, 32, 64-bit. We plug the microcontroller with the evaluation board on our mini-hill board. If there is no board that fits, we can put it next to the mini-hill board and wire it with those cables, or we create a little adapter board, a passive adapter board for your chip. Then we connect the pins of the microcontroller over this patch panel with the system, with the test system. with the IOs. So typical signals are digital, analog, SPI, so all the low-level bus systems, I2C, CAN, LIN, of course PWM for the motor controls, and so on and so on. So now on this side, on the side of my test system, I need three things. I need the drivers to be integrated for the signals. Then I need environment simulations to simulate the motor, the temperature, the battery, whatever your system is made of. Yeah, because if there is no simulation, you cannot run your system and test your system. And the last thing you need is test cases. The biggest effort goes into the environment simulation. Test cases are relatively simple to do if you have the right tools, but you need the environment simulation, and we also have the right tools for the environment simulation there. So now we're focusing on what do you need on the test system side to do this. So whatever goes into this chip is modeled in our case. We have a simulation and test modeling tools, so we can model the structure and the behavior for the simulation and for the tests. And from there, we generate C code, we compile it, we flash it to the test system. And then it's the complete test and the simulation is executed on this chip here. It's executed on this chip and not on your PC or in your laptop or in the continuous integration server, because we need hard real time. For example, for a motor control system, you need 20-30 kilohertz simulation, and this cannot be done on a PC or something like that. So you need hard real time. Then when the test runs, we generate logs, we transform the logs into diagrams, and then we go back and we learn and iterate. So you change your test system or you change your system under test, it's always the same process here. So now, why do we want automation and continuous integration to support this? We want this for automation because automation makes sure that every change is tested, and automation saves time. It gives you speed, a lot of speed actually. So how does continuous integration work? Every developer commits his changes to the source code management repository. The source code change triggers the continuous integration server. So the continuous integration server monitors the source code repository, and then it automates builds, it automates the tests, and it automates the releases. What does this? What are the principles behind this? Every change is integrated and tested. So every change, whenever you commit. So you should commit early and often. So whenever you have a package ready, after a couple of hours, for example, a bug is fixed, you've written a test case, so check it in and make sure that the continuous integration server has the opportunity to test this. Why do you want to do this? You want to fail fast. After minutes, hours, you still know what you changed, and the probability that there are many other commits is very low. So after half a year, you do not know what you did half a year ago. You might already be in a different project, and there are probably 500 or 1,000 other commits on the same repository, so you have no idea where to start to find this error. So that's crucial for continuous integration. So bugs can be detected and fixed very early, sometimes within minutes, without even anybody else noticing it. So hardware on the loop on your desktop, that's what it looks like. You have a mini hill board attached to your laptop, and that's it. You model the test cases and you execute the tests and the simulation. So that's a typical setup for one project or one developer, maybe with 2 or 3 projects on his desktop. If you have a bigger team or bigger projects with more developers, or if your development team is distributed, you want, so worldwide, location-wise distributed, you want continuous integration. This helps a lot. So every code change is built, tested, and delivered within minutes. We have, for example, here 8 different mini hill projects in a 19-inch rack. So they can all run in parallel. Whenever you commit a project, all those projects are executed. The tests for those projects are executed. That's a typical setup for many projects with a mini-hill. So by doing this, really every code change of every developer for every project, no matter where the developers sit, can be tested within minutes. So now I'm going to show you a little demo. I have brought you a demo setup for a motor control application. The system under test has a STM32 controller. That's this one here. It's a STM32. That's the test system. And those wires here, you can see here. So the system under test runs a motor control application for BLDC motors. So it generates 3 PWMs. Then the test system measures those PWMs with 10, 20, 30 kilohertz. So 20,000 times a second, executes a simulation step, calculates the new speed of the system, and generates 3 Hall signals according to the speed of your system, to the simulated speed. In this case, those are 3 Hall signals simulated as digital outputs, inputs. This could also be for field-oriented control analog signals. Then we simulate the temperature sensor as analog value, and then we have the UART to change the motor speed to get error messages from the system and so on. So basically it's a simple motor control application. It's not very far from reality, so it's a pretty decent demo. So let's have a look at electrical level what a test case looks like. So for example, here in this case, we have the 3 PWMs that are generated by the system under test. They are measured. The simulation is executed and generates those 3 Hall signals as digital outputs. And we have the UART here to control the speed. Here we have a bit more coarse-grained picture to show you the test cases. Here again the PWMs, here the Hall signals. You can see how the Hall signals follow the PWMs. Then the UART to control the speed, the simulated temperature as analog value. Those are the equivalency classes and the boundary values for those test cases. And here it's just an analog output from the simulation to know what the simulated speed is, because that's something hard to read here. Here we just take the current frequency of the motor and put it to an analog output, because then we can get a correlation between what in the test system and the system under tests happens and bring those things together. So for example, in this case, we make a speed change with the UART, and the speed changes in the system under test. This leads to, because it's a closed loop simulation, this leads to a slower test system simulation here. You can see how the simulation goes down and down and down. And here we are, the speed is 0. Then the next test case would be a full stop for a temperature error. In this case, that's a temperature error. It's below the error temperature. So what we expect is that the PWMs go off immediately after, let's say, 100 microseconds, and that they stay off for a certain time until the motor is stopped. And here you can see it's a real closed loop simulation, because the motor is getting slower and slower. Because of its inertia, it keeps running a little bit. So then we have a thing like temperature, a warning temperature, a limp home functionality. So the system just gets us a little bit slower, maybe to recover from a problem, a heat problem or something like that. We do not want to shut down it immediately, just if it hits a warning temperature. And in the end, we want the system to recover. So those would be typical 4 test cases that can be run on the mini-hill. So now let's have a look at my continuous integration setup for the demo. I have the laptop with my development environment for the test cases and the system under test. I develop the simulation and the test models. Then I commit everything to the Git source code management system, also locally on my computer. I have a Jenkins CI server, continuous integration server, also locally on my computer. You can use any continuous integration server, doesn't really matter which technology it is. In my case, I have a continuous integration Jenkins continuous integration server. And then the continuous integration server builds, flashes, and runs the tests. This does not need to run on your laptop. It can also run on your server infrastructure. And then the test is executed on the Mini-Hill board, and the results are again propagated to the Jenkins server, and we then transform the logs into diagrams. So that's how we develop the tests. And if you change anything in your system under test, it's exactly the same process. So the Git source code management recognizes a change. So the Jenkins server checks it out, whether it's a test or the system under test, doesn't matter, and builds, flashes, and runs the test. So you can also run always a back-to-back test for the same system under test. If you make changes to your test system, you know that your test system is still okay. And if you change your system under test, you can see that everything is okay if you do not change the test system. So that's a really, really nice process there. So let's have a look at the real demo. I'm going to show you how we model this. So I'm going into the demo model. So everything inside this box here, everything that's yellow, is generated and compiled and flashed to this microcontroller here. Down here we have the analog, the digital inputs and outputs, the UART, we have a whole generator, we have a duty capture unit and so on. So the duty capture unit captures the PWM values, feeds it into the motor simulation, and the motor simulation calculates the new speed and propagates it to the whole generator. The whole generator generates those 3 digital outputs according to what a sensor would do. Then the motor simulation, of course, I need a behavior. We can integrate manual C code. We can integrate generated models from other tools like Simulink. But you can also directly model simulations, especially event-driven simulations, as state machines. So that's a real state machine. Editor, deep editor. If we change the duty cycle, the new duty is memorized as a member variable, and then we calculate the new speed, and we generate with the whole generator, we propagate the new speed to the whole generator. So set speed or set direction, so we can make easily error injection, failure injection here. And from those state machines, we also generate C code, so it's completely executable. So the last thing I need the test case. So for the test case, I need also behavior, not only the structure. The test case could be done with a state machine. That's how we did it at the beginning. But the state machine is not very efficient to create test cases. So we created a deeply integrated language. Another language, it's called Cage, for case generator. And with this language, we can decide asynchronous steps for our tests. So a step always consists of actions and reactions. And so, for example, I want to stop and check the time measurement. So I stop the time measurement and I expect that a certain time is elapsed, or that in this case a certain speed is reached, or something like that. So the steps themselves, we try to make them atomic so that we can reuse them. And one level above, we have sequences. In those sequences, we can integrate steps and other sequences to deeper test cases. In this case, for example, this test sequence is made out of several steps. And then on top level, we can add all those test cases into test suites to have, for example, all the motor control tests in one test suite. So that's how we develop the simulation and the test cases. Now I can run everything from here, but we also have a graphical user interface, a separate one to run this directly without the development environment. So for example, for quick production tests or for the developers. And now if I run the test case, I can connect to the test system, and now I can run the test cases, and they really run now on the mini-hill board. And I get all the results as sequence diagrams. So here you can see the diagrams with the results. So that's not the generated diagram as in the development environment, but the real diagram from the test execution. So the last thing I wanted to show you is the automation. Now I'm going to change a little bit of code in my system under test. So that's now your system under test, basically. That's an example system under test. I'm only using the same development environment. So now I'm changing something here. I'm introducing a bug. And what I expect is that my continuous integration detects the change and starts the mini-hill test. So let's introduce a bug by making the duty cycle a fixed value. Here you can see it's everything checked in to Git. I add it to index. I commit the bug. Let's call this bug. And now I commit it, and I immediately switch to the continuous integration server. Now I'm switching to the continuous integration server. And as you can see, it already detected the change in the Git repository. It starts to check out the project, assemble the project, flash it new. You've seen the LEDs here going off. System under test test system is flashed. System under test is flashed. Now the test run is in progress. Test is running. A couple of seconds usually it needs. In this case, it's a very simple demo, so this might take a while for a real-world project. And now we see that the project is yellow. So why is it yellow? Because some test cases failed. Let's have a look at the test cases. So 3 test cases are wrong here. So limit temperature and motor control speed. Those are the test cases that failed. So let's have a look at what really happened by clicking at the log. So motor demo integration test. Here you can see that the test failed and expect failed because the speed was wrong. So I click on the expect that failed, and in the development environment I see exactly the position, check speed, where the problem occurred. So that's how we do continuous integration for embedded systems. So I hope you enjoyed the webinar. If you have any questions, don't hesitate to ask me. You can send me a direct email or also go via our website. Have a nice day and hope to see you soon. Bye-bye.